The science of keeping it cool. Why do electronics get hot and how do various cooling methods work? Almost every single piece of modern electronics generates heat whether we notice it or not. Without properly managing that heat, our electronic systems would destroy themselves, or conversely, we'd be severely limiting our computing capabilities. The average TechSpot reader will think, of course, CPU and GPU cooling, but why does RAM not need fans to keep it cool? Why is there such a huge disparity between the performance of a mobile processor and a desktop processor even though the dies are pretty similar in size? Why have recent performance gains from new generations of chips started to slow down? The answer to all of these has to do with heat and the physics of how digital computers work on the nanoscale. This article will touch on the basic science of heat, how and why it is generated in electronics, and the various methods we have developed to control it. It's getting hot in here. The basics of heat. If you remember high school physics, heat is just the random motions of the atoms and molecules that make up our world. If one molecule has a higher kinetic energy than another molecule, we say it is hotter. This heat can be transferred from one object to another if they come into contact until the two reach equilibrium. That means the hotter object will transfer some of its heat to the cooler object, with the end result being a temperature in between the two. The time it takes to transfer this heat is dependent on the thermal conductivity of the two materials. Thermal conductivity is the measure of a material's ability to conduct heat. An insulator like styrofoam has a relatively low thermal conductivity of 0.03, while a conductor like copper has a high thermal conductivity of 400. At the two extremes, a true vacuum has a thermal conductivity of 0 and diamond has the highest known thermal conductivity of over 2000. One thing to remember is that heat always goes to cold, but there's no such thing as cold. We just view things as cold if they have less heat than their surroundings. Another important definition we'll need is thermal mass, which represents an object's inertia against temperature fluctuations. With the same sized furnace, it is much easier to heat a single room in a house than it is to heat the entire house. This is because the thermal mass of a room is much less than the thermal mass of an entire house. We can put all these concepts together in the simple example of boiling water. When you turn on the stove, the hot flame will come into contact with a cooler pot. Since the material making up the pot is a good thermal conductor, heat from the fire will be transferred into the water until it boils. The time it takes to boil will depend on the method of heating. For more on this story, visit the news article link.